Welcome to this week's first lecture in EE 557. In the last lectures, we have seen the concept of controlled Markov chains, and today's topic is going to be the continuation of that. We are going to learn some terminology about the type of different Markov chains. So far we have seen how to specify a Markov chain. So we need to specify the initial state distribution that is called P0. And this P0 is composed of the elements P01, P02, going until P0I. And each of these P0Is are the probability that X0 is equal to I. Okay? And then we need to specify the transition probability matrix, TPM. That is called P, and it's composed of elements Pij. This is an I by I matrix. And each of these Pijs are the transition probabilities. And it is probability I have xk plus 1 is equal to j, given xk is equal to I. Whenever we specify such two quantities, then we specify a Markov chain. And in the last lecture, we have learned how to calculate the arbitrary state the distribution of an arbitrary state xk. Okay? And we have seen that this happens to be P0 times the transition matrix to the kth power. And we have learned that actually the transition matrix to the kth power is nothing but the k-step transition probability matrix. And we have also seen the recursion pk plus 1 is equal to pk times p. And actually this equation is how we derived this general formula. And then we concentrated on the properties of this pk as k increases. And we asked the following question: does P infinity exist? If I let k go to infinity here, then does P infinity exist or not? We asked that question, and when P infinity exists, is it unique? And it is independent of the initial state distribution P0. So we have answered those questions, and actually we have defined a type of Markov chain for which those questions are answered affirmatively with an answer yes. Okay, and that is the ergodic Markov chain. Okay, a Markov chain is ergodic by definition if and only if P infinity exists. Okay, and if and only if as well P infinity is unique and independent of the initial state distribution P0. We have defined the ergodic Markov chain, and then we have talked about the property of an ergodic Markov chain. So remember, there was a property which is quite difficult to understand. So, and actually here I would like to write it once more because I seem to have made a mistake there. So the property of an, sorry, I cannot find it. Okay, the property of a Markov chain, ergodic Markov chain is this. Probability xk is equal to I is equal to limit as n goes to infinity 1 over n, k equals to from 0 to n minus 1, indicator function xk is equal to I. Okay? So on the left-hand side, I had a deterministic quantity, and it was a probability. And on the right-hand side, I have a stochastic quantity, because it depends on the realization of the stochastic process, xk. So when I try to equate a deterministic quantity to a stochastic quantity, there are generally some rules of probability for these equalities. And here, it is usually said that this equality should be satisfied with probability 1. In this lecture, we are going to see or we are going to try to understand what this with probability 1 might mean. Actually, we are going to see an example where this equality is not satisfied, and I will try to explain this equality concept here. So here in this equation, there is a mistake actually. Okay, so I have forgotten to write something here, and in my notes I'm going to correct them, and I will publish those notes, replace the old notes with the new one. And actually the correction is going to be quite simple. So here, the thing that disturbed me, or actually the thing that made me realize my mistake here, is that the left-hand side here is dependent on k, the time index. Okay, this probability is dependent on time. This is the ith element of this pk vector, and it depends on time, as you see. On the other hand, the right-hand side, when the limit n goes to infinity, it doesn't depend on k. It might look like it depends on k, but k is the argument of the summation here. So summation actually makes us get rid of all k dependence from this quantity on the right. Okay? So this equality is not correct because the left-hand side depends on k, the right-hand side does not. It doesn't make much sense. Okay? So here the correction is actually just this. Here, either I need to make a summation type or integral type of argument to get rid of k from the left-hand side, and actually the correct correction would involve something else. It is going to be limit as k goes to infinity, probability xki is equal to just this. Okay? And remember, in the last time I have showed that this probability of xki is nothing but the expected value of the indicator function xk is equal to I, and there I need to have limit k going to infinity as well. Okay? So I need to have this equality. So in that case, this limit makes us get rid of k, and equality might hold, because both sides, equality actually makes sense in that case. Both sides are independent of k. So here, this quantity is pki, the ith element of the vector pk. So since in an ergodic chain, this limit always exists, this limit is going to be p infinity I. Okay? And in an ergodic chain, this p infinity I should be equal to this limit. For every realization, for every realization of the stochastic process xk, these averages, the average number of times that xk becomes I should be equal to the p infinity I, the stationary probability that the state is at the ith state. Okay? So now we're going to continue with our theory, and we're going to try to establish some sufficient conditions for a Markov chain to be ergodic. And in the last lecture, we have seen one such property, one sufficient property. If lambda is equal to 1, we know that this transition probability matrix would always have an eigenvalue at 1. If lambda is equal to 1 is the only eigenvalue of P on the unit circle, and if lambda equals to 1 is not repeated, multiplicity of lambda is equal to 1 in the characteristic polynomial and in the minimal polynomial as well, is not repeated in d of s of p, then these two implies that Markov chain is ergodic. We have seen this in the last lecture. Okay? So this is a sufficient condition, and actually there is a theory of Markov chains which would always try to establish such a condition. Okay, and let us try to understand what P infinity should be when it converges. If P infinity exists, then that means that this limit as k goes to infinity pk, or limit as k goes to infinity p0 times p to the k exists, okay, then we know what p infinity should satisfy. Then I can take the limit of both sides of this equation, and it would give me p infinity is equal to p infinity times p. Okay, so if the limit exists, if p infinity exists, then we know that p infinity is a left eigenvector of p for the eigenvalue lambda equals to 1. Okay? And when p infinity exists, we are going to ask the question of uniqueness. Is this unique? Is this p infinity unique? Can there be more than one vectors which would satisfy such an equality? Okay? And this case is a sufficient condition for the uniqueness as well. The Markov chain is ergodic. That means that p infinity exists. So this is if and only if p infinity exists and p infinity is unique. Okay? So this is a sufficient condition. And now we are going to try to establish another sufficient condition by looking at the connections of the Markov chain. Okay? And that is going to be the concept of reducibility of a Markov chain. So let us look at the definition. A Markov chain is called reducible if and only if it is transition probability matrix TPM P in Rn by n, let us say that there are n states, can be put into the form P equals to, if I can put the transition probability matrix of a Markov chain in the following form: a matrix P1, a matrix P3, and a matrix P2. And this lower left block is completely zero, where P1 and P3 are square matrices, possibly by a reordering of the states, by a reordering of the states. Okay? So this is the concept of reducibility for a Markov chain. If we can bring the transition probability matrix of a Markov chain into this form, it might be already in this form, or we might play with the order of the states, indices of the states, and we can try to bring it in this form, into this form. And if it can be brought into this form, then we call the Markov chain a reducible Markov chain. Okay? The definition continues, and actually what is going to be important for us is the reverse of this property. So we are going to call it irreducibility. A Markov chain is called a Markov chain, let us say, which is not reducible, is called an irreducible Markov chain. It's called an irreducible Markov chain. So in this definition, we are defining two things: reducibility of a Markov chain and irreducibility of a Markov chain. We call the Markov chain reducible if its transition probability matrix is in this form, or it can be brought into this form by reordering or re-indexing the states. And if we cannot do that task, then we're going to call the Markov chain as an irreducible irreducible Markov chain. And in general, irreducibility is the good property that we would be interested in. Okay? Reducibility is not usually good for ergodicity. Okay? So let us now look at an example. So I want to keep this property here. Still. Example. So the Markov chain that we are going to consider is going to have the following three states. 1, 2, 3. Well, there is a probability, self-probability here, 0.7, and here to state 2 with probability 0.3, and I have here the probability 0.8, and here the self-probability is 0.2. And I would have here just probability 0.4, 0.3, and 0.3. Okay, so this is my Markov chain here, and now I need to consider whether this Markov chain is irreducible, reducible or not, or irreducible or not. So the first thing that I'm going to do is to calculate the transition probability matrix of this Markov chain. So remember that in this case the transition probability matrix is going to be a 3 by 3 matrix because we have 3 states, and let us write the transition probability matrix for the first state, which means the first row here. Okay, so the self probability 1, 1 is 0.7 and 1, 2 is 0.3, and there is no direct transition from 1 to 3. That means that this probability is 0. So you see that the sum of the first row elements is equal to 1. Because this is a stochastic matrix. Let us look at the state 2. In the case of state 2, we have the self probability 0.2, and the probability to state 1 is 0.8, and I would have 0. And finally, I have the state 3, which has 0.3 from 2, sorry. Yes, no, that's not correct. That is going to be 0.4, 0.3, and 0.3. Okay? So you see that row sums are all equal to 1, meaning that this is a stochastic matrix. And I see that here, this transition probability matrix, this TPM, is not in this, definitely in this form. Okay? So here, let us try to, so here I will try to change the order of the states. Okay? To check if this TPM can be brought into the form for reducibility. Okay? So here you need to actually remember one thing. In this matrix, the rows represent xk and the columns represent xk plus 1. Okay? And this is the state 1, state 2, and state 3. This is xk plus 1 is equal to 1, 2, 3. All right? So now I'm going to change the order of the states into 3, 2, 1. Okay? Into this matrix, I will first write the third state probabilities for xk, and then I will write the second state probabilities, and then the first state probabilities. So let us write P for this new order of states. Okay? And in that case, I would have the order. This is 3, 2, 1, and I would have here xk, and this is xk plus 1, 3, 2, 1 here. Okay? So the probability of 3 to 3 is this element, 0.3. 3 to 2 is 0.3, and 3 to 1 is 0.4. Okay? 2 to 3 is 0, and 2 to 2 is 0.2, and 2 to 1 is 0.8. And I would have the first state probabilities. 1 to 3 is 0, 1 to 2 is 0.3, and 1 to 1 is 0.7. Okay? So now you see that this new transition probability matrix is exactly in the form that is required in the definition. Okay, so we see that this is my matrix P1, square matrix P1. It's a 1 by 1 matrix. And this is the matrix P3. It's a 2 by 2 matrix. Okay, and the rest is actually equal to 0. So what is the conclusion here? The conclusion is that this Markov chain is reducible. So now what does this reducibility mean intuitively? So here we see that if I start my state when I am at state 1, I can never go to state 3. Okay, because this element will always be equal to 0, and if I am at state 1, I will never be able to go to state 3. Similarly, if I am at state 2, I can only go to state 2 or state 1 with non-zero probability, and I cannot go to state 3. Okay, so if I start my Markov chain from these two states, from either state 1 or from state 2, I will never be able to go to state 3 in one step. Okay? What about in 2 steps? So these elements here, these 0 elements, would mean that the states in this group corresponding to these 0 elements, when I start my Markov chain from there, I will never be able to go to the first state group here. Okay, corresponding to this P1. All right. What about in 2 steps? So I can actually look at P square. This is a 2-step transition probabilities. So sometimes I might not be able to go to one of the states in one step. I might need to have to cross other states in order to be able to reach the other state. Okay? So what about in 2 steps? So in order to be able to calculate that, I'm going to use this form, P1, P2 and P3 and 0. So 2-step transition probability matrix is P1, P2, P3 square. Okay, this is 2-step transition probability matrix, and if I do this multiplication, I would get P1 square here, and I would have 0, and I would have P1, P2, and plus P2, P3, and I would have P3 square. So you see that in the 2-step transition probability matrix, these transition probabilities are also 0. So I will not be able to make the transition from 1 to 3 in 2 steps either. Okay? This single-step transition probability matrix shows that I will not be able to make this transition in 1 step. Okay? So, and these zeros in the 2-step transition probability matrix show that I will not be able to go from 1 to 3 in 2 steps because those probabilities are 0, and I will not be able to go from state 2 to 3 in 2 steps either because those probabilities are going to be 0. So I can actually repeat this idea over and over to calculate pK, and I can show that for this type of transition probability matrices in this form, there will always be equal to 0, and I would have here P1 to the K, I would have here P3 to the K, and I would have here another matrix. Okay? So you see that if I have a reducible Markov chain, then there is always a subset of the states for which, if I start my states from that subset, I will never be able to reach the other states. Okay? I will only be able to, so from state 2, I can only reach state 2 or state 1, and from state 1, I can only reach state 2 or state 1. I will never be able to reach state 3 when we start the Markov chain from this subset of states. Okay? So in a reducible Markov chain, there is always a subset of states for which, when we start the Markov chain from those states, we would always remain in the same set of states. We will never be able to reach the other states. Okay? So this tells us that for a reducible Markov chain, I can actually find a subset of states, a sub-Markov chain, in which if we start the original Markov chain, we will never be able to go out of that sub-Markov chain. Okay? So that is the meaning of reducibility. Reducibility means the existence of a sub-Markov chain which behaves like a Markov chain itself when we start the original Markov chain from the states in that sub-Markov chain. Okay? So that is the intuitive meaning of being reducible for a Markov chain. And for an irreducible Markov chain, no such sub-Markov chains would exist. So now let us write this as a remark. In a reducible Markov chain, there is always a smaller or a sub-Markov chain satisfying the property that if we start the state of the Markov chain, in the sub-Markov chain, then the state never leaves the sub-Markov chain. The state never leaves the sub-Markov chain. Okay? And in this example, what is that sub-Markov chain? It is these states 1 and 2. Okay? So my sub-Markov chain would be here. Okay? So in this sub-Markov chain, if I start my state from the sub-Markov chain, the state will never be able to go back to the state 3. Okay? We will always remain in the states 1 and 2 if we start our state in this sub-Markov chain. All right? And this is seen from the transition probability matrix. If it is in this form, then we can say it. And we showed that the transitions can never happen in any finite number of steps. Okay? So then, what does it mean? So intuitively, that is what irreducibility is. For reducibility, there will always be a subset of the states from which I will not be able to, or the Markov chain will not be able to reach the other states. Okay? So what about the intuitive meaning of irreducibility? For an irreducible Markov chain, there is no subset of those states which satisfy that property. So that means that in an irreducible Markov chain, we will be able to reach from any state to any other state. Okay? Irreducibility means that there is no reducible and there is no such sub-Markov chain, meaning that all states are reachable from all other states. So now let us write this as a theorem. It is not difficult to prove this theorem, and actually an idea is given for the proof in the book, but I will not prove it in the class. A Markov chain is irreducible if and only if every state J can be reached from every state I. Possibly by passing through other states. Okay? So the transitions do not have to be in one step. Okay? So an irreducible Markov chain really does not have to have all non-zero elements in its transition probability matrix. Some transitions might not be possible in one step, but they have to be possible for some finite number of steps. Okay? So now let us look at an example of an irreducible Markov chain. So in this case, I will give you an example of a Markov chain with 4 states. So I would have state 1, state 2, state 3, and state 4. And I would have the following probabilities. 0.1, all self-probabilities are 0.1. And from 2 to 1, I have 0.9 probability, transition probability. From here, I have 0.9. From here to here, I have 0.9. And from here to here, from 4 to 3, I have 0.9. Okay? So now the question is this Markov chain reducible or irreducible? So here the thing that I need to check is that can I actually find the transition or transitions with non-zero probabilities from every state to every other state. From 1 to 1, I can actually transition. What about from 1 to 2? 1, 1 is okay. And what about 1 to 2? I cannot directly go in one step. I cannot directly go from 1 to 2, but I can go from 1 to 4. Let us write it as an okay transition. And similarly, I can go to 3 by making first a transition to 4 and then to 3. So 1 to 3 is also covered. And then from 3, I can go to 2. So I can go from 1 to 4 in one step. I can, with non-zero probability, I can go from 1 to 3 in 2 steps. And I can go from 1 to 2 in 3 steps. Okay? So from 1, I can go to all states. Okay? What about from 2 to 1? 2 to 1, there is a direct transition. From 2 to 2 is also covered. 2 to 3, I can first go to 1, and I can then go to 4, and I can go to 3. 2 to 3 is okay, and 2 to 4 is also covered. Okay, so you see that by looking at the Markov chain in this manner, for this Markov chain, you can show that you can go from any state to any state. Okay, so that means that actually this Markov chain is irreducible. Is irreducible. So here note that this doesn't mean that all of the transition probabilities, all of the single-step transition probabilities are non-zero. This doesn't mean that all of the transition probabilities, one-step transition probabilities, are positive. Okay? So some of the transition probabilities, for example, the transition probability from 1 to 2 is actually equal to 0. One step, because there cannot be a one-step transition from 1 to 2 in one steps. Okay? So this index is equal to, this element of the one-step transition probability matrix is equal to 0, okay? But I know that if I increase the allowed number of steps, then I can eventually reach the state 2 with non-zero probability, okay? What does that mean? From 1 to 2, how many steps is required? So first I need to transition from 1 to 4 with 0.9 probability, and then I need to transition to 3 with 0.9 probability, and then I need to transition to 2. So you see that I need to make 1, 2, 3 transitions. So here I can say that I cannot transition from 1 to 2 in 2 steps either. So this is also equal to 0, but I see that here in the 3-step transition probability matrix, the first row, second column element is actually going to be strictly larger than 0. Okay? So I would have this 3rd-step transition probability. This element would be non-zero because I can transition in 3 steps from 1 to 2. So that means that for a Markov chain, when I look at these matrices and each element of these matrices, I would always find the power of this matrix for which that element has a positive probability. Okay? That is going to be written as a remark. A Markov chain is irreducible if and only if for all I and j, okay, there exists a power k which is larger than or equal to 1 such that p to the k ijth element is positive. Okay? Because I know that I can actually go from any state to any other state in an irreducible Markov chain. That means that there should always be a power, a non-negative power, for which that element of the k-step transition probability matrix corresponding to the transition from I to j should be positive. If I cannot find such a k, then that means that from one state to another state I cannot go. However many steps I take, then that means that the Markov chain is irreducible. There is a sub-Markov chain in that case. All right? So we are going to see that irreducibility is a good property for ergodicity. Usually, actually I need to say from the start, if a Markov chain is irreducible, this doesn't mean that it's going to be ergodic. Okay? Similarly, if a Markov chain is ergodic, in general this doesn't imply that the Markov chain is irreducible. Okay? There is no direct equivalence between irreducibility and ergodicness. Okay? So from the start, we eliminate that possibility. But we will see that irreducibility is going to be one of the conditions that is required for ergodicity. That is going to be one part of the sufficient conditions for ergodicity. Okay? But there is no direct relationship in general. All right? But irreducibility is still good. So here let us look at an example. So this example is going to be an interesting Markov chain. The transition probability matrix is just equal to the identity matrix. Okay? So I have this identity matrix. So then let us try to understand this Markov chain. Is this Markov chain reducible or irreducible? In this Markov chain, from the first state, I can only go to the first state, and I cannot go to the second state. Okay? And actually, you see that this Markov chain is in the form of a reducible Markov chain. And if I try to show it as the block diagram, then I would have the first state and the second state. From first state, I can only reach the first state with probability 1, and from the second state I can only reach the second state with probability 1. Okay? So this Markov chain is like two individual Markov chains with one state combined together. Okay? The states are not interacting. They are not going from each from one to the other. Okay? So it is like two Markov chains, two individual Markov chains combined together. So obviously this Markov chain is reducible. And you see that this P matrix is already in the reducible Markov chain form. So now let us try to look at these pKs. So let me say that P0 is this. P0 is, let us say, 0.8 and 0.2. So there is a 0.8 probability of being in state 1 for the Markov chain, and the other initial probability is 0.2. Okay? Then what is going to happen to pK? I know that pK is equal to, I have P0 times P to the K, but P is identity matrix. That means that pK is equal to P0 for this Markov chain. So we see here that this probability distribution of the states never changes. If initially we are at state 1, we remain at state 1. If initially we are state 2, then we remain in state 2. So these probabilities, this probability distribution will never change. So there will always be 0.8 probability of being in state 1 and 0.2 probability at being state 2. Okay? So what can I say? Limit as k goes to infinity pk. pk is a constant vector. It's always equal to p0. So as a result, this is equal to p0. It always exists. And I know that this is by definition my p infinity. Okay? So for this example, p infinity is equal to p0. So I know that p infinity always exists in this case, because this limit always exists. P infinity exists, and P infinity is equal to P0. So can I say that this Markov chain is ergodic? For ergodicity, we need the existence of P infinity, but we also need that this P infinity, when it exists, should be independent, should be actually unique, and it should be independent of P0. So do we see that independence here? Definitely not. P infinity is exactly equal to P0. It really depends on the initial state distribution. That means that this Markov chain is not ergodic. Markov chain is not ergodic. I know definitely that the ergodicity does not hold. Okay, because of non-uniqueness of P infinity. So remember, so what can be P infinity? Any initial condition, any possible initial condition would be a P infinity candidate in general. Okay? So here let us look at the equation given like this. P infinity times P is equal to P infinity. So which P infinity values would satisfy such an equation? I know that in this case, capital P is identity, so the equation turns into P infinity is equal to P infinity. Any vector would satisfy this equation, okay? So this is the characteristic equation of the vector P infinity when it exists, and I know that there is not a unique vector which would satisfy this equality. And actually, because P is identity, any vector would satisfy this equation. Okay? So so here there is no existence problem, there is the uniqueness problem. And this uniqueness problem is caused by the reducibility of this Markov chain. We are going to see that if a Markov chain is irreducible, then there is only one and only one vector which would satisfy this type of equality. Okay? So this equation is going to have a unique solution if the Markov chain is irreducible. Okay? So here I would like to use this example still for another purpose. I would go back to these equations here, and I would like to show you that this property is not satisfied because this Markov chain is not ergodic. Okay? And in order to be able to do that, I will calculate the left-hand side and the right-hand sides here. That is why I kept that equality there from the start of the lecture. So here let us look at first Pxki. Pxk is equal to I. In this case, let me say I is equal to 1. Okay? Looking at the other probabilities, it's going to be the same thing. Okay? Because Markov chain, it's kind of symmetric for both states, except for the initial distribution. So let us look at this probability. This is the first element of pk1, and I know that pk1 is equal to p01, okay? p01, and that is equal to 0.8. This is a constant value independent of k, okay? And that means that limit as k goes to infinity, pxk is equal to 1 is going to be 0.8 here. The left-hand side of the ergodicity equation is going to be equal to 0.8. Now let us look at the right-hand side. Okay? Right-hand side is a stochastic variable, a random variable. Okay? So let me look at this xk is equal to 1 indicator function. This is nothing but 1 if xk is equal to 1, and this is nothing but 0 if xk is equal to 2. Okay? In this case, I have this. Here, in this Markov chain, I don't know what xk is. Xk is a random quantity, and I know that x0 is equal to 1 with probability 0.8, and x0 is equal to 2 with probability, here I would write this with probability abbreviations here, with probability 0.8 and with probability 0.2. So then what is the probability that xk is equal to 1 and xk is equal to 2? I know that if this Markov chain is started from the state 1, it's going to remain at state 1. Okay? And if it is started at state 2, it's going to remain at state 2. Okay? So here I can say that xk is equal to 1 with probability 0.8, and xk is equal to 2 with probability 0.2. Because the Markov chain continues in the state where it is started. Okay? But you see that xk is still a random variable. Okay? So now I'm looking at a single realization of this Markov chain. Okay? And then we'll calculate the right-hand side there. So I have x0, x1, going until x infinity. This is a single realization of the Markov chain, and I know that it is random. Suppose that with 0.8 probability, the Markov chain starts at 1 and it continues at 1. Okay? So for all time instance, it is at 1. And with 0.2 probability, it is at 2. It is started at 2 and it continues at 2. Okay? So if it starts at the state 1, what is indicator xk is equal to 1? So if the Markov chain starts at the state 1, then this indicator function, I'm setting I is equal to 1, is going to be equal to 1 for all k. Okay? Because in that case, xk is equal to 1 for all time, so this is going to be equal to 1 for all k. Okay? And if on the other hand, the other event happens, x is started at the state 2 and it remains at state 2, then what is going to be xk is equal to 1? In this case, this event never happens. That means that this is going to be equal to 0 for all k. Okay? So what does that mean? So for a single realization, either all of these indicator functions are equal to 1 or all of them are equal to 0. Okay? So what about these summations? 0.8 probability, 0.2 probability. 1 over n, I have k equals to 0, n minus 1. Indicator function is 1 with 0.8 probability. So this is going to be equal to, there are n terms here, and divided by n, this is going to be equal to 1. Okay? And it's going to be independent of n now. And with 0.2 probability, it's going to be 1 over n, k from 0 to n minus 1, 0. Because the indicator function is 0 with this probability, then this is going to be equal to 0. Okay? We see that both of the values are independent of n here. And then what is going to happen when I take the limit as n goes to infinity? In that case, the right-hand side is going to be equal to this one with probability 0.8, and the other one, it's going to be equal to 0 with probability 0.2. Okay? So this is a time average ensemble average. Time average and a stationary or the steady state ensemble average. So we see that this is my right hand side. What about the left hand side? Left hand side was equal to 0.8 with probability 1. Okay? So I see that this equality is not satisfied. So this is my left hand side. It is 0.8 with probability 1, and the right-hand side is either 1 with probability 0.8 or it is 0 with probability 0.2. And I see that 1 is never equal to 0.8 and 0 is never equal to 0.8. So we see that this equality is not satisfied for this non-ergodic chain. So the time averages do not give us ensemble averages here. So I have the ensemble average here 0.8, and the time average is either 1 or 0, depending on which state that the Markov chain is started at. Okay? So here, I try to give you a type of intuition. I really do not know if I was successful or not, but here, for this ergodic chain, non-ergodic chain, the time averages are not equal to ensemble averages, and that is actually why this Markov chain is not ergodic. But here, the thing that we need to pay more attention to is that this equation have a non-unique solution for this reducible Markov chain. Okay? For an irreducible Markov chain, this can never happen. And we're going to write this as a lemma. Let P in Rn by n be the TPM of a finite state Markov chain. Markov chain. The Markov chain is irreducible. Is irreducible if and only if there exists a unique row vector pi, which is equal to pi 1, pi 2, going until pi n, such that pi times p is equal to pi, where all pi i's are positive for all I, and summation I from 1 to n, pi I is equal to 1. So for an irreducible Markov chain, we would have a unique solution to the equation describing P infinity when it exists. So when P infinity exists, there is only one place, one and only one place to converge to. When Pk converges to P infinity, which means when P infinity exists, there is only one place, one and only one place, a unique place for P infinity to converge to. That is really a good property. So now let us look at some examples. And there is an if and only if here. Okay? I have here this if and only if in this lemma. So I have irreducible property if and only if this equation P is unique and Pi's are positive and summation of Pi's is equal to 1. Okay? I have this if and only if for a Markov chain. So if this property is satisfied, it is also irreducible. There is also the backwards implication, which is correct. All right? If I can find a unique P which would satisfy these properties, then I can also say that the Markov chain is irreducible as well. Okay? So there is a double-sided implication in the lemma. Let us look at an example. So I have P given as 0.8, 0.2, 0.3, and 0.7. So now what can you say for the reducibility or irreducibility of this Markov chain? So you see that its transition probability matrix, all of its elements are positive. So I know that from all states I can go to all states with non-zero probability. So that means that this Markov chain is irreducible. That means that when I try to find the solution of the equation pi p is equal to pi, I will only find a single vector, and a single vector would satisfy these properties. Okay? So here I need to solve this eigenvalue, eigenvector equation. This is a left eigenvector of P corresponding to the eigenvalue 1. Okay? So remember how in 501, how I found eigenvectors. If I have an equation, what I would do was write this in this form and try to find a non-zero vector which would be in the null space of this matrix. Okay? Here I will do the same. I will actually take this part to the left-hand side, and it's going to be pi minus I is equal to 0, and I will try to look for a non-zero vector in the left null space of this matrix. So let us write P minus I. That means that I will subtract 1 from the diagonals. I would have minus 0.2, 0.2, 0.3, and minus 0.3. Okay? And I will try to find a non-zero vector, a row vector, which would give me 0 row vector when I multiply it with this matrix. Okay? So that vector, I can see that it's going to give me a 0 linear combination of these rows. So P is that is pi, not P. Pi is proportional to, let me say, 3 and 2. If I multiply the first row by 3 and the second row by 2, and if I sum them, I would get the 0 row vector. That is what being inside the left null space of a matrix means. So, but we know that this vector, this unique vector, should have all pi's non-zero. They are non-zero here, but their sum is not equal to 1. But here I know that if I find a non-zero vector, I can always normalize the elements of that vector such that the sum of its elements is equal to 1. Okay? And therefore our pi is going to be 3 over the sum of these elements, 3 over 5 and 2 over 5. So I would have 0.6 and 0.4. So that is my unique pi vector. So that is the unique left eigenvector of this matrix, which would satisfy these properties. And this is happening because the Markov chain is irreducible. So what does this mean in terms of ergodicity? For ergodicity, I need two things. P infinity should exist, and P infinity should be unique. It shouldn't depend on P0. Okay? And here, for an irreducible Markov chain, I see that if P infinity exists, it is going to be unique. But the question is, does P infinity exist or not? Okay? So, if in addition to irreducibility, I can make sure that P infinity exists, then there is only one place to converge. One and only one. There is only a unique place to converge here. That means that if I can ensure that Pk converges to P infinity, that limit is going to be unique. So the question is, how do we make sure that Pk converges for an irreducible Markov chain? That is what we are going to do in a few minutes. Okay? So here let me solve another example and show you something interesting. I will call the earlier example as example 1, okay? And this is going to be example 2. And I will have an example 3 later. So here let us say that P is equal to 0.5, 0.501, okay? So let me try to draw you this Markov chain. I have from 1 to 2, 0.5 probability. Here I have 0.5, and I would have the probability 1 here. So is this Markov chain reducible or irreducible? So you already see that this matrix is in the form of a reducible Markov chain. Okay? And here you see that if I start the Markov chain from the state 2, then it's going to remain at state 2. That means that this Markov chain is reducible. Is reducible. All right? So there is an if and only if here. So if the Markov chain is reducible, then the negative of this thing should hold. Okay? Because this is an if and only if. All right? So do you think pi is going to be non-unique in this case? Let us look. So here I have pi times p is equal to pi, and I would have pi times p minus identity is equal to 0. Let us calculate p minus identity, which is equal to minus 0.5, 0.5, and I would have 0, 0. So now I will write a left vector here. I will multiply this matrix from the left by a row vector, and that should give me 0. Okay? So I see that that left vector is going to be proportional to 0, 1. Okay? If I normalize this, it's going to be 0, 1. So can I find another pi vector which would satisfy these properties? So I cannot find another pi vector which would normalize to 1, which would satisfy that equation. So in this case, pi is unique. But the Markov chain was reducible. So according to this lemma, shouldn't it be that pi isn't unique? The answer to this lies at these conditions. Here, the left-hand side tells us that pi is unique and pi is composed of positive elements. Okay? So sometimes for reducible Markov chains, pi can be unique, but there would always be 0 elements in pi. Okay? That is why this really doesn't violate this lemma. Okay? So sometimes, let us write this as a remark. So for reducible Markov chains, so sometimes there can be non-uniqueness, and sometimes there will be uniqueness, but with 0 elements. Okay? So that is the property of reducibility. When the Markov chain is reducible, sometimes pi can be unique. So there is only one place to converge, but some elements will always be 0. Be 0 in that case. Okay? So do not think that when pi is unique, we need to have irreducibility. Okay? There is no implication, because on the right-hand side, I have also the condition of pi I being strictly positive. Okay? And do you think this Markov chain is ergodic? There is only one place to converge. Pi is unique. Okay? So do you think this Markov chain is ergodic? Look at the eigenvalues of the P matrix. Eigenvalues are 0.5 and 1. So there is only one eigenvalue on the unit circle, which is 1, and furthermore that all of the other eigenvalues are not on the unit circle, and 1 is its multiplicity is 1 in the characteristic polynomial. So you can actually show that this Markov chain is ergodic. And here you see that this is not, you see that it is not correct that if you have an ergodic chain, then this doesn't mean that you have an irreducible Markov chain. But this is not correct. Okay? So now let us solve one more example here. Example 3. So P is given as 0, 1, 1, 0. If I draw you this Markov chain, it would be like this: 1, 2. The probability from 1 to 2 is 1, and probability from 2 to 1 is 1. Do you think this Markov chain is reducible or irreducible? Can I reach from 1 to 1 again? From 1 to 1, there is no direct transition, but I can first go to 2 and then we'll come back to 1. Okay? So I can reach from 1 to 1, and I can reach from 1 to 2 definitely, and from 2 to 1 I can reach, and from 2 to 2 I can reach in 2 steps. Okay? That means that this Markov chain, I will just write MC here, is irreducible. Okay? That means that there is a unique pi vector in this case. Okay? So let me try to find P minus identity is minus 1, 1, 1 minus 1. And you see that pi is going to be proportional to 1, 1. And normalize this. So pi is equal to 0.5, 0.5. All right? In this case, pi is unique as well. And now I would like to concentrate on these two examples. Example 1 and example 3. Which one is, we will see that only one of the Markov chains is going to be ergodic between example 1 and example 3. Okay? So let us go back to example 1. In example 1, I have this unique pi, which is 0.6 and 0.4. So suppose that I start the initial state distribution of this Markov chain at 0.9 and 0.1. Okay? So when I now look at P1, P2, P3, etc., there is only one place to converge if this pk converges. Okay? So when I calculate this P1, this is P0 times the matrix P, you get 0.75, 0.25. Okay? And if I calculate P2, multiply this with P from the right again, and you will get 0.675, 0.325. If I continue in this manner, P3 is going to be 0.637, 0.363, and P4 is going to be 0.62, 0.38. So if I continue in this manner, this P10 is going to be 0.6 and 0.4 approximately. Okay? And so we see that when I choose P0 like this, the sequence converges to this single place to converge. Okay? So now the question is, what happens if I change this P0? When I change this P0, so you can try it in MATLAB yourself, when I change this P0, you would always see that whatever you choose your P0, you're going to converge to that unique place to converge. Okay? So here we would have P infinity limit as k goes to infinity pk is nothing but pi. that unique vector you calculated there. So in this case, if you try to understand whether this Markov chain is ergodic or not, in this case, the Markov chain is ergodic. Okay? It is irreducible and ergodic. All right? Now let us go back to example 3. Example 3 is also irreducible. Okay? And there is also a unique pi vector. So if pk converges, there is only one place to converge. There is no other destinations. Okay? But the question is P convergent? Is pk convergent? So I have P0 is equal to, let us say, 0.9, 0.1. All right? Then P1 is going to be P0 times P, which is 0.9, 0.1 times that matrix. 0, 1, 1, 0. And if you do this multiplication, you're going to get 0.1, 0.9. This is P1. Okay? What about P2? So you see that this matrix multiplication, it is doing nothing but interchanging the elements. All right? So here, P2 is going to be 0.9, 0.1. P3 is going to be 0.1, 0.9, etc. We are going to go until infinity like this. So there is only one place to converge here, but pk is not convergent. Okay? So what can we say about the ergodicity of this Markov chain? Well, in this case, the Markov chain is not ergodic. Okay? And actually you see here a periodic type of behavior in these probabilities. Okay? So here you see that if we start this Markov chain, it's first going to go to 2 and then to 1, to 2, to 1, to 2, 1, etc. So there is a periodic behavior inside the Markov chain dynamics. Okay? And this is the problem here. If the Markov chain can be irreducible, but if it has some periodic dynamics in it, it might not be ergodic. Okay? If it doesn't have any periodic dynamics, like the case of this dynamic, then this Markov chain, then it's going to be ergodic. Okay? So if you take an irreducible Markov chain, if you make sure that that Markov chain doesn't contain any periodic dynamics, then the Markov chain is going to be ergodic. Okay? So now we are ready to define the periodicness for a Markov chain. And then we are going to combine irreducibility with non-periodicness, and we are going to end up with our sufficient condition for ergodicity. Definition. A Markov chain is called periodic if and only if its TPM P can be put into the form P is equal to 0, P1, 0, I would have this, 0, 0, P2, 0, 0. So I will continue until 0, 0, 0 here, 0, Pn minus 1, and I have Pn, 0, 0. Where the 0 blocks on the diagonal are square matrices. So now let us look at the definition of periodicity. A Markov chain is called periodic if and only if its TPM can be put into the form given like this. This is called the block circulant matrix, and it has this type of form where the 0 blocks on the diagonal are square matrices, and obviously in general the TPM itself does not have to be in this form. You can rearrange the states, indices of the states, and sometimes you will be able to bring the Markov chain TPM into this form. So this is like reducibility definition. The TPM does not have to be in this form, but you need to be able to put the TPM into this form by reordering your states. So here I can actually add possibly by reordering the states. Okay? So here, when we look at this transition probability matrix, then there are some groups of states, okay? First group, second group, third group, etc. We are grouping our states here, all right? And when I start the Markov chain in the first group, then the Markov chain state can only go to the second group. Okay, because only these can be non-zero. When I start my Markov chain in the second group of states, the Markov chain can only jump, transition to the third group, etc. Okay, and when I start the Markov chain from the nth group, then the Markov chain can only jump to transition to the first group. Okay, so this type of periodic behavior is required for a Markov chain to be called periodic. Okay, so here this P matrix is already in that form. The first group of states is state 1, and the second group of states is composed of state 2. And when we start at state 1, we go to state 2 in one step, and the second group. And when we start at state 2, we go to the first group of states. That is why this Markov chain is periodic. So let me try to show you just another example of a periodic Markov chain, and in this case I'm going to construct the periodic Markov chain myself. All right. The first thing before that I will just write, if a Markov chain is not periodic, if a Markov chain is not periodic, then it is called aperiodic. Okay, so we just add an A into the adjective periodic, then we have an aperiodic Markov chain. So let us look at an example. So I would like to construct a 4-state Markov chain. Okay? Xk is in 1, 2, 3, 4. All right? And let me try to construct the periodicity in the following way. Let us say the states 1, 2 is the first group of states. Let us say that from this first group of states, I can only go to 3. Okay, and this is my second group of states. Let us say that this is the third group of states, 4, and from this I can only go to 1, 2. Okay, let me try to form a P matrix that would have this type of periodicity. From 1 to 2, I can only go to 3. That means that I need to have here. From 1, I can only go to 3. That means that this probability is going to be 1. And from 2, I can only go to 3. That means that I can only have this transition probability. And from 3 to, I can only go to 4. That means that the third row is going to be like this. And from 4, I can go to either 1 or 2. Let me write that I can go to 1 with 0.9 probability, and I can go to 2 with 0.1 probability, and then I would have 0, 0. So this is a periodic Markov chain, and in this case, you would have the period different than 2 actually. Okay. So in this case, you might expect complex eigenvalues. So, and these groups here, would be formed like this. Okay? So I would have, this is my zero blocks here. This is my P1. 1, 1. These P's do not have to be square. Oh, the diagonal zeros needs to be square matrices. So you see that this P1 is not a square matrix. P2 is 1, and P3 is equal to 0, 0, 0.9, 0.1. And you see that this n, in this case, it is the period of the periodicity. So you would expect eigenvalues at e to the 2 pi over 3 j kind of places on the unit circle. I hope it is true. That is what I remember, but check if it is true or not. So now, when we take an irreducible Markov chain, if we exclude the periodicity, if we make sure that the Markov chain is not periodic, then we would expect that Markov chain to be ergodic. Okay? So here, the convergence or the divergence of pk is caused by the presence of periodicity. So if we take an irreducible Markov chain and if we ensure that it is also not periodic, then we are going to have ergodicity. This is going to be given by a theorem. If a Markov chain with TPM P in R n by n is irreducible and aperiodic, then limit k goes to infinity, the transition matrix P to the power k would go to a matrix called pi, a constant matrix called capital Pi, where all rows of the matrix pi are equal to the unique row vector small pi satisfying pi is equal to pi p with pi I positive for all I, and I is equal to 1 to n, pi I is equal to 1. So if we have irreducibility, and if we exclude periodicity from that irreducibility, then we would get this limit becomes capital Pi, and all rows of this matrix becomes this small pi, which is the unique destination of pk. Okay? So we would get this limit p to the k becomes this capital Pi matrix, and I would have here all rows of this matrix equal to just this unique row vector, which would satisfy this equation, unique left eigenvector. So we will finalize this theory with a corollary. If a Markov chain with TPM P in Rn by n is irreducible and aperiodic, then limit k goes to infinity, which is p infinity, pk, is equal to pi for all P0 in Rn. Or let us say for all P0. Okay? Because in this case, I need to ensure that P0 should satisfy P01. I will remove just the Rn, because this has to be always a positive vector. For all initial conditions is sufficient. So if a Markov chain is both irreducible and aperiodic, then we would have this convergence. So P infinity would always exist, and it would be equal to pi. And I know that pi is unique because of the irreducibility, then the Markov chain is ergodic. In other words, Markov chain is ergodic. So it's not really difficult to see this. If you accept the theorem, then it is really easy to prove the corollary. Let us look at the proof. So limit, I will calculate P infinity. P infinity is, I know that it is P0 times P to the, limit as k goes to infinity, pk, and I know that limit k goes to infinity, pk is p0 times p to the k, okay? And I can take the limit into the matrix term there, p0 times limit k goes to infinity, p to the k, and the theorem tells us that this limit is fixed and it is equal to this capital pi matrix is equal to P0 times capital pi, okay? And what is this P0 times capital pi? Let us try to write this. P0 is composed of P01, P02, going until P0n, and this matrix has rows pi, etc., okay? Then this is nothing but a linear combination of the rows of this matrix, okay? So this is equal to P01 times pi, P02 times pi, going until P0n times pi, all right? So here, then I can take pi parentheses here, and these are just scalars, I from 0 to n, P0i, times pi, and I know that summation of the P0i elements should be 1 because this is a probability distribution, and therefore this is equal to 1, which is equal to pi, okay? And this is, you see that this is independent of the initial probability distribution P0 here, all right? So now so that actually finishes our theory related to the Markov chains. So what did we see here? In general, we have started with the so-called irreducibility. Irreducibility is a good property for ergodicity, but it is not actually sufficient nor it's necessary for ergodicity. We have seen the irreducibility, and we have seen that irreducibility implies that there is only one place to converge for the probability distributions pk, okay? And all elements of that single pi vector would also be positive. But we have seen also that in the case of irreducibility, we might have periodic behavior and we might have aperiodic behavior. So we have seen that periodic behavior makes pk divergent. It really doesn't converge anywhere when we have a periodic irreducible Markov chain. So then we excluded by this theorem from irreducibility the periodicity. Okay? And when we combine irreducibility and aperiodicness, we have obtained our sufficient condition. That implies ergodicity. Okay? So if we have a Markov chain which is both irreducible and aperiodic, then we are going to have an ergodic Markov chain. And in that case, pk is always convergent, and furthermore, there is only one place to, since there is only one place to converge, then we have our ergodicity result. pk is always convergent because we assume the aperiodicity. Remember, periodicity makes the pk vector non-convergent. Okay, so the convergence comes from aperiodicness, and the unique destination comes from the irreducibility. When we combine these properties, we get ergodicity. Okay, so this completes this long lecture. I hope it's not too complicated. So we have three properties: ergodicity, irreducibility, and periodicity. I hope I did not confuse you in this lecture. That's all for this one. Thank you for tolerating. Bye.